Hello, everyone. Welcome to the Test of Time Award presentation. To just give a little background, the annual Supercomputing Test of Time Award recognizes an outstanding paper that has deeply influenced high-performance computing and appeared in an SC program 10 to 25 years ago. The award, therefore, acts both as an incentive for researchers to send their best work to supercomputing, as well as a calibration for understanding which papers have had truly lasting influence. This year's award goes to a paper presented in SC98. And hopefully some of you remember SC98 was in Orlando, Florida. It introduced multi-constraint graph partitioning algorithms that load balance multi-phase computations where each mesh element or graph vertex may require different resources, such as CPU, memory, network bandwidth, etc. These algorithms, which are multi-level, have been incorporated into the METIS and PAR-METIS graph partitioning software, which have been applied throughout the community in HPC. The codes are destined to have widespread continuing application. So it is my distinct pleasure to introduce the two authors of that seminal paper. Awardee George Karypis is a distinguished professor and chair of digital technology in the Computer Science and Engineering Department at the University of Minnesota and a senior principal scientist at AWS AI. His interests span data mining, high-performance computing, information retrieval, collaborative filtering, bioinformatics, cheminformatics, and scientific computing. He has co-authored over 300 papers on these topics, along with 2 books, and regularly serves on program committees for IEEE, ACM, and related conferences. For those of you who are starting early in your career, George has an H-index of 103 and over 83,000 citations, according to Google Scholar. The second awardee is Vipin Kumar, a real dear friend of mine, is a Regents Professor at the University of Minnesota, where he directs the Data Science Initiative. He has headed the Computer Science and Engineering Department and directed the Army High Performance Computing Research Center. His interests span data mining, high performance computing, and their applications to climate and healthcare. He has authored over 400 papers and has co-edited or co-authored 10 books. His many awards include the 2016 IEEE Sid Fernbach Award, and he's a fellow of the AAAS, ACM, IEEE, and SIAM. And just to put a finer point on his legacy, Vipin has an H-index of 127 and over 113,000 citations. So again, it is my honor to present George, who is going to give the talk today.
Thank you, Rupert, for that introduction and the kind words. So I guess I have, so for those guys, we haven't connected the dots, right? So that was a 98 paper that was done the year after I graduated, actually 2 years after I graduated, right? And Vipin was my PhD advisor, right? And that was something that was done when I was a research associate at the Army High Performance Research Center at the University of Minnesota. Okay, now I have to put my old man's glasses so I can actually see what I'm presenting here. So, as Rupert said, I'm George Karypis. I'm a professor at the Department of Computer Science at the University of Minnesota. And I'm also on leave at AWS, where I'm lead a team of scientists developing distributed methods for training very large neural networks. So both Vipin and I would like to thank the awards committee for the great honor and this recognition. So, so being recognized by the supercomputing community is very special to me. And the reason for that is my very first paper, right, research paper, was actually published in supercomputing in 1992, right? So that was a paper on tree search, IDA star, on CMD architectures. That was back on the connection machine 200, right? And since that point in time, I've been, part of the supercomputing community, ever since, right? As a point of reference, the SC in '92 actually took place in Minneapolis, and it was a very nice small conference. Soon afterwards, supercomputing became a very large conference, and Minneapolis doesn't have a large enough convention center to actually host a supercomputing conference. Okay, so the reason I'm here is for the work that we did in 1998 on multi-level algorithms for multi-constraint graph partitioning. Okay. So that work was designed to load balance multiphysics and multi-phase scientific simulation HPC systems. And as a trivia, so here's a screenshot of the paper. As in trivia, SC98 was the first and last supercomputing conference in which they were not accepting PDF or PostScript submissions. During SC98, you had to actually submit your paper in HTML, right? And that did not go very far because people very quickly realized, HTML at that time was not very well suited, for entering mathematical equations, right? And so I was trying to find a screenshot of the paper that was actually a PDF, right? And I could not find it. And then I remember that '98 was that year that all of us had to suffer with HTML submissions. So when I found out that we got the Test of Time award, we also found out that we have to give a presentation. And the very first thing I did was I actually went and tried to look for my 1998 slide deck, right? Hoping if I could find that slide deck, then I can just make the same presentation again. And believe it or not, I did find it, right? So there were actually 42 slides in that slide deck, right? I can't believe I gave a presentation using 42 slides. Probably I skipped every other slide. Not only that, there's a lot of text in those presentations. And actually, if you look at, I don't know how sharp of an eye you have, there's some kind of very cheesy graphics over here. I think that was kind of the early days of PowerPoint usage, right, which everybody wanted to be creative, right? So I decided not to recycle the slide deck, and then I was thinking about, how to structure my presentation, and then David Keith sent an email a couple of days ago, actually, yeah, and he had a very interesting quote over there that I'm kind of, verbatim quoting it here. I know that David Keith is not here in this room today, so I'm safe to quote him, without him complaining. And his quote was something like that, right? That's a user of METIS, like numerous members of the HPC community, an admirer of your paper, it is delighted to see it identified for the renewed attention for those who may not appreciate its origins. After all, some young users were in diapers then, okay? So it's very hard to see, how many people we have and how many of you guys are young people, right? And thinking this is a hybrid conference, right? But if it was everything in person, I would have asked for a show of hands to see who was in diapers back in 1998, okay? But David's comment kind of inspired me of structuring the talk around the lines of providing you an overview, right? Presenting the work in the broader context of what came before, right? What came after, and what everything else was done in this area, right? So I cannot have a talk about graph partitioning without having a slide that defines the problem of graph partitioning, right? And in order to do that, I did I went back to a slide that I first created in 1995, and I took a screenshot of my standard graph partition definition slide, and I present over here, right? So for those who are not familiar, the problem of graph partitioning is given a graph and a number k. What we want to do is partition the verts in the graph into k parts, such that each part has roughly the same number of nodes, same number of vertices, and the number of edges that straddle partitions, right, is minimized. Right? So it's a problem that has a single constraint, that of balancing the number of nodes, and has a single objective, that of minimizing the cut. So that problem falls into the category of NP-hard problems, and in order to solve them, we use heuristic algorithms. So then the second slide that is also very customary in a graph partitioning presentation is, why do we care about graph partition, right? So why graph partitioning is an important problem, right? And the reason that graph partitioning is important, again, one of my trusted slides, right, is that it has a wide range of applications across different domains, right? It can be used to map computations of parallel computers. It can be used to compute field-reducing orderings for direct methods. It can be used to simplify or accelerate floor planning, placement, routing in VLSI circuit design, in data mining to do clustering, and so on. Right? So this is a problem that is, has a wide range of applications, and the number of applications keep on increasing. Okay, so so then the next thing that people usually ask me, or at least once they know that I work on graph partitioning, and especially now that I've been doing that thing for a few years, is how we got into the graph partitioning problem in the first place. Okay. So already I told you my first paper was on IDA star on SIMD machines, okay? So my second paper, if I remember correctly, was on dynamic programming on systolic arrays. I know that systolic arrays are making a comeback. I guess I must have been 25 years ahead of my time, right? But the fifth paper was on parallel sparse Cholesky factorization, okay? So that was a paper that was published in '95. And at that point in time, what we did is we developed a scalable parallel formulation of Cholesky factorization for distributed memory architectures. That formulation was able to achieve 20 gigaflops on a 1024 processor Cray T3D. So for those who are not familiar with Cray T3D, T3D was the very first MPP system that Cray developed. And that level of performance, getting 20 gigaflops for that computation was unheard at that time for this type of problem, okay? So of course nowadays probably my iPhone can do it, but that's a different story, all right? So, excuse me. So the underlying algorithm that we used to perform the Cholesky factorization was based on multifrontal method. Right? And the multifrontal method, what it is, it relies on nested dissection ordering of the sparse metrics in order to structure the computation in a way that exhibits concurrency. Okay? So in the nested dissection ordering, the way it works is given the graph representation of a matrix, what nested dissection ordering does, it finds a balanced vertex separator. Right, so a vertex separator is a set of vertices in the graph that once I remove it, I split the graph into two parts, right, with nothing between them. And a balanced vertex separator is the one that the two parts that I have created have roughly the same number of nodes. What nested dissection does is once it finds the vertex next, the vertex separator, then it reorders the metric such that the vertices of the first part are ordered first, the vertices on the second part are ordered second, and the separators are at the end, right? And it recursively does the same thing for both of the two parts in that, in the two-way partition that it computes, right? So, in the picture that I have over there, that nested dissection ordering, it looks at the top right part over there, right? So in order to compute the nested dissection ordering, what you have to do is you have to use a graph partitioning algorithm to do that, okay? So what happened then in 1995, we had a very scalable way of computing Cholesky factorization, right? And then the bottleneck became that of computing a nested dissection ordering, right? So the thing that we were interested in is how can we develop an algorithm to compute a high quality nested dissection ordering fast, right? And that's why we started looking into graph partitioning, okay? So it has nothing to do with graph partitioning itself, it has to do with Cholesky factorization. So, excuse me, so if we look at the state of the art in graph partitioning in 1995, right, you can see that a set of methods existed. And those methods were coming primarily from three communities, right? So the primary consumers of graph partitioning in 1995 were scientific computing, high-performance computing, and VLSI CAD, right? And each of those communities was doing its own research and developing methods. And over the years, a different set of methods have been developed that were specifically designed for each of those domains. Okay? So looking at the state of the art in 1995, the methods based on multi-level recursive bisection were the ones that were looking at the most promising. Right? So multi-level framework is an approach that I will roughly call it a simplify and conquer approach. in which, what you do is you start with your original graph, and then through a set of operations that usually involve contracting of vertices, you generate a progressively smaller set of graphs until you get to a very small graph. In that small graph, you compute initial partitioning. And then once I have that initial partitioning, then I project that initial partitioning back to the original graph through the intermediate graphs. And in each of those projection steps, I further refine and improve the solution as it comes up from the course's graph. Okay? So, and the multi-level approaches, represented the state of the art of the time when it comes down to graph partitioning. Okay? So, by the way, for those who are not in the know, well, it's an interesting expression. So the 1995 method that I have listed over there, right? That one corresponds to the algorithm developed by Bush Hendrickson and Rob Leland, right? That was made available in Chakra, right? And that algorithm received the Supercomputing 2014 Test of Time Award, right? So it's interesting that graph partitioning so far has received 2 Test of Time Awards, in the Supercomputing conference. So, so we started working on serial multi-level graph partitioning algorithms, and we ended up creating, what ended up becoming the METIS software for graph partitioning and field-reducing orderings. So the initial research that we pursued to focus on developing different heuristics for the coarsening phase that makes it easy to find high-quality solutions during the initial partitioning phase, and developing incremental refinement algorithms that allow us to perform the refinement extremely fast, and also optimizing for field-reducing orderings, for computing nested dissection. Right, so here's a result slide that is, again, circa of 1995, that compares the performance of multi-level nested dissection versus the nested dissection against the multiple minimum degree ordering, which was, at that point in time, one of the state-of-the-art approaches. We can see over here that, so this is a relative plot. Lines below 1 means better than multiple minimum degree. Lines above 1 means we're doing worse than multiple minimum degree. So you can see that, METIS nested dissection is always better than multiple minimum degree, and it's considerably better than spectral nested dissection. Plus, it's much faster than spectral methods, right? So at the end of this work, we, to a large extent, achieved the initial goal of being able to compute very fast nested dissection orderings for our Cholesky factorization work. So after that initial research, right, we continued to working on graph partitioning, and end up releasing a couple of versions of METIS. So METIS 2.0 included an algorithm to compute K-way partitioning really fast by having a linear time algorithm for doing that. The 3.0 of METIS, improved the quality of the field-reducing orderings, and also allowed allow the algorithm to compute partitioning of meshes, finite element meshes directly, right? However, the major change happened with version 4.0, and that is a release that directly relates to the Test of Time Award that I'm talking about today, right? So the 4.0 release is actually implementing the algorithms in the 1998 paper. So to give you some context about the work that led to the research that we did in 98, so up to the 3.0 release, or at least all the way up to, including 3.0, METIS, as well as the other, partitioning packages that were available at the time, were able to solve problems that involved a single balancing constraint, right? It was balancing the number of nodes in the graph, or if the graph had the nodes with weights, it was balancing the sum of the weights of the nodes in each partition, okay? However, as HPC systems were getting larger and more mainstream, people wanted to solve, progressively more complex and more, and new types of problems, right? And those complex and new types of problems could not have been effectively load balanced, right? With the partitioning method that were available at that point in time, right? And to give you some idea about some of those problems, excuse me. So one class of problems are those that involve multi-phase computations, right? So those are the scientific simulations that they perform over let's say, a finite element mesh. But in that finite element mesh, different parts of the mesh are involved in computations at different phases, and there's an explicit synchronization step between those phases. Right? So in order to be able to balance those computations, what you want to do is you like to be able to balance, to distribute the phases equally across the processors. Right? So you want to compute a single partitioning that simultaneously balances all the phases. Okay? So to give you an idea about what that means, is I had that color-coded picture, and each color corresponds to a phase. And what I want to do is to assign to each processor the same amount of each color, so that things are balanced when I perform the multi-phase computations. Right? So another case involves heterogeneous workloads involving tasks requiring different amounts of resources. Right? So the simplest example of that are computations whose tasks perform different amount of computation and require different amount of memory, right? So, and if I have a computation like that, using the traditional partitioning algorithm, I have a choice of either partitioning with respect to the computation, okay, or partitioning with respect to the memory, right? But either way I do it, I'm going to have loaded balance with respect to the other resource, right? So, and that will either limit the size of the problem that I can solve if I'm partitioning with respect to the computations, right? Because then I will be limited by a high water mark in terms of, which machine, runs out of memory, right? Or I will have load imbalance if I'm going to partition with respect to the memory, right? So ideally what I want to do is I want to compute a single partitioning that simultaneously balances the computations as well as the memory requirements in each partition, right? And, and yet another example that is related to the multi-phase computations, the computation involves overlapping meshes, right? So those are different meshes over the same physical domain in which as part of the computation there's an interpolation of data between the different meshes, right? So when I compute on one mesh, then I have to use some information from that mesh to project them to the other mesh over the same domain in order to compute and so forth, right? A way of partitioning those computations need to be able to balance every mesh, minimize the communication in each mesh, and ensure that each processor is assigned parts of the meshes over the same physical region, so that I can minimize the amount of time I spent in communication for that interpolation step. Okay? So those are the kind of computations that we saw coming up in '98. And one of the advantages that we had in releasing a software like METIS is that we did not actually have to go out and look for those problems. People were coming to us saying, hey, can you solve this problem? Can you solve this problem? Can you solve that problem? Right? And after looking at collecting some of those requirements, we realized that there is a need to develop an algorithm, right, that is able to handle an arbitrary number of balancing constraints, okay, which led to the '98 work, right? So, excuse me. So the paper that we presented in '98 generalized the standard min-cat balance partition problem to the one that seeks to compute a min-cat partitioning that simultaneously balances multiple constraints. Okay? It analyzes the feasibility of being able to actually compute those partitionings and provide some guarantees and some bounds. And the third thing that it did is actually develop algorithms that will actually compute those partitions, right? And made those algorithms available in METIS 4.0. Okay? So, so that was in '98, right? So since we released that work, I mean, I came to realize that the whole concept of multi-constraint partitioning, or partitioning required to balance multiple constraints, it's actually very predominant out there. And there are many problems whose solution requires a multi-constraint formulation, even when that multi-constraint formulation is not directly obvious, right? And that work on the multi-constraint partitioning has led to significantly other work, subsequent work both by us and as well as other teams on developing, additional and better, multi-constraint algorithms, right? So since '98, researchers have used multi-constraint METIS to solve many of the problems that I described earlier, right? Researchers improved on the algorithm for computing the multi-constraint partitioning solutions, and also extended multi-constraint partitioning to new domains, right? And here's like a screenshot of some papers related to that. But my favorite one is the one that is right at the top, right? Is actually people are employing multi-constraint partitioning to do congressional district redistricting, right? And the reason for that is they treat the thing to be as an unbiased way of doing that, right? So you can try to prevent, the gerrymandering, right? And this is something that I became aware about 4 or 5 years ago when someone from the state of Minnesota, he was getting ready for the redistricting that will happen after the census. They were building the tools and they came across, some people applying methods like that. And then they connected the dot that, oh, those guys are from Minnesota, we should probably go and talk to them, right? So this is actually a very good application of multi-constraint partitioning. So, another application of multi-constraint partitioning that is actually much closer is something that has actually involved the last 12 months or so. So as you guys have seen my affiliations, I have both a University of Minnesota affiliation as well as a AWS-AI affiliation. The reason for that is because I'm on leave at AWS-AI for the last 2.5 years or so, right? So as part of that effort, I lead a team over there that is developing a deep graph library. So deep graph library, or DGL, is a framework for training and using graph neural networks. So, and as part of that effort, what we have been looking is we have been working on developing a distributed DGL framework that will allow us to train very large graph neural networks on graphs involving several billions of nodes. Okay, and training GNNs, that's an entirely different talk, right? It's a non-trivial process, especially if it involves mini batch kind of training approach, right? And the reason for that is that the mini batches are generated via doing a random sampling on the graph, and the size of the resulting computational graph is highly dependent on the topology of the graph over which you do the sampling. Okay, so as a result, if you do it if you take a standard partitioning algorithm like METIS and partition the graph, right, and then you have own a compute kind of approach to actually parallelize the computations, you may end up assigning to a particular processor part of the graph whose resulting computational graph has significantly more computations than the other processors. Okay, so one simple way to to solve that problem is, instead of doing a graph partitioning approach to partition the graph, to just randomly partition the graph, right? But anybody who does random partitioning, they know that all of a sudden the locality goes away. So you sacrifice balance for increased communication overhead. So what we're doing over there is we're trying to formulate that as a multi-constraint partitioning problem. And actually, if you notice, there's a version of METIS that actually on GitHub that has a DGL tag to it, right? That is specifically optimized, for these type of workloads. And what we're able to achieve is is the performance of the rightmost bar over there is a result of the multi-constraint METIS. Is able to outperform, either the standard METIS partitioning or the standard random partitioning, right? So it's able to lead to balanced computation and also still retain locality that minimizes the communication overhead. So, however, there's a bigger context to the work that I just described, and involves several parallel efforts and activities, right, that led to and benefit from the 98 paper. Okay, okay, so I have about 15 minutes. And I will try to quickly go through that slide, but by the time I'm done, that slide will be full, right? So in addition to the work we have been doing on METIS, there's another stream of work that involves, parallel version of METIS, PAR-METIS. PAR-METIS is a MPI-based distributed implementation of METIS, or distributed version of METIS, that we started developing in '97 and has been actively developed on and off since then, right? And METIS is PAR-METIS implements all the algorithms that METIS has, right? plus some additional algorithms that are specifically optimized for dynamic computations, right? So, that work is done by Kirk Schlegel, right? And by the way, LinkedIn is the best place to find screenshots of your former students. So if you're a student, though, make sure you put a good picture over there, because you never know if your advisor will pull one and put in a presentation, right? So, and Kirk actually developed a whole slew of algorithms for dynamic repartitioning, multi-level algorithm for dynamic repartitioning. And actually, this is work that, Kirk actually collaborated with Rupak and Lenny on that, when, I guess some time ago, right? So back in 98, 99 timeframe, right? So, so in addition to that, we have been working on multi-level algorithms for hypergraph partitioning. Hypergraphs is a generalization of a graph, and the generalization is that instead of the edges involving a pair of nodes, there is a concept of a hyperedge that has more than two, potentially more than two nodes, right? So, and those hypergraphs are well suited for modeling VLSI circuits. Because a gate can be driving multiple inputs, so not just one input, and that forms a hyperedge. And this is work that was done by Rajat to begin with, and then continued by Selva on developing multi-level algorithms for hypergraphs. And the interesting multi-constraint connection is the work that Selva did in the context of FPGAs. So there's a need to partition in very large circuits on an FPGAs as a way to quickly prototype those things, and also to quickly simulate, to make sure that they actually emulate, to make sure that they actually work correctly. And FPGAs have a small number of different resources, and what you want to do is you want to be able to take your circuit and partition it to multiple FPGAs so that each of those resources is never gets oversubscribed. Okay, so this is an instance of a multi-constraint partitioning problem that is a bounded capacity as opposed to a balancing version of that. And the algorithm that we developed in 98 paper went to inform the work that Selva did on his work. Then another spread of work is something that was done by another graduate student, Dominic, that develop multi-threaded versions of METIS. So we have a serial METIS, we have a distributed memory METIS, but back in '97, right, our processors had only a single core, right? Maybe sometimes we'll be lucky if our processors had two cores, right? But middle of 2000s, all of a sudden our processors had more cores and keep on having more and more cores, right? So there was an opportunity over there to exploit the hardware, right, in order to develop more efficient partitioning algorithms, as opposed to entirely relying on a distributed memory formulations, right? So Dominic took up on this challenge and developed very scalable multi-threaded algorithms for both partitioning and ordering, and those things are available as part of the multi-threading METIS. Now, on an entirely different line of work, the multi-level algorithm and also the multi-constraint algorithm are also relevant for clustering purposes or for network science kind of applications in which you would like to cluster social networks. And Cluedo is a clustering toolkit that we developed in which it's version 2 implemented a whole slew of multi-level algorithms for clustering. And related to that is some additional work that Dominic did on Nerstrand. Nerstrand is a multi-threaded modularity optimization algorithm using a multi-level paradigm, and can actually scale to pretty much achieve linear speedup and lead to high quality modularity-based solutions, right? So besides that named work, right, so there's some other lines of work that the team has been doing over the years. So Irene has been looking at actually some very challenging multi-constraint problems, and those are the problems in which the constraints are dynamic and depend on each other. And also, architecture-aware partitioning. And then Amin was looking at, how to take the multi-level algorithms and extend them so that it will operate on some of the emerging graph architecture, graph types back in the middle 2000s that had a parallel degree distribution. Okay? So, but I would like you guys to understand that, that the work that I just described to you is just a part of a much larger and collaborative effort, right? So this is a screenshot I got from Wikipedia yesterday that describes graph partitioning and lists some of the different tools that, collaborators and researchers, fellow researchers, across the world, have developed. Related to partitioning, and many of those things are very actively developed, right? And we're making great progress. So I'm trying to conclude so I can leave some minutes for questions. So all the places you'll go. So Dr. Seuss is my favorite book. It's something that I actually give to each one of my PhD students when they graduate. So this is called the rite of passage, to get your signed version of Dr. Seuss' book. And so since I started looking at the graph partitioning problem 25 plus years ago, we have come a long way, right? But I think there are many places that we can go from here, right? So back in 2016, even though that survey was in the making a few years prior to that, Aidan, Henning, Ilya, Peter, and Christian put together a survey on recent advances in graph partitioning and future research directions, right? So for those who are very much interested in graph partitioning, this is a required reading, even though that survey is about 6 years old now. It's still fairly up to date, and I know that the team is working on an updated version of that. And one of the good things about that survey is it has a couple pages at the end that it actually, the team pulled all of us. I was involved, Dominic was involved, Bruce Hendrickson were involved in kind of charting out some of what we consider to be some of the future research directions. And I would like to quickly kind of summarize them, right, into, there are research opportunities on advancing graph partitioning for graphs that they're difficult, right, and have complex structure, right? 25 years ago, the graph we used to care about, at least in the HPC side, was finite element meshes. Those are very simple graphs, right? Nowadays, we're interested about natural graphs. Those are, much more complex graphs, right? But the nature of the graphs, it can change over time, right? So in developing algorithms that are well suited for them is an important problem. The other part has to do with the new parallel computing architectures, right? So how do we take advantage of them to develop highly scalable parallel formulations of our graph partitioning algorithms? Then new applications, new problems come up that have new partitioning requirements, and that itself can lead to new research. To a large extent, the multi-constraint work was a case of that. And then there's always an opportunity to improve the quality of the algorithm that we currently have, right? Especially by exploiting the connections between theory and heuristics, right? And this is something that I'm truly looking forward in the near future to have some additional test of time awards related to partitioning in supercomputing, right? And to conclude, so I'd like to thank all of my students, and collaborators, right? I'd like to thank, Vipin, right? Even though he is a co-author on that paper, he has been a mentor and, and an awesome advisor, right? And, of course, the whole thing would not have been possible, without many collaborators and mentors, outside, students and advisors, advisees, right? And the whole graph partitioning community, for someone looking from outside, may think as a bunch of people that seem to be competing with each other. Actually, this is not true. Everybody is actually working very nicely with each other, and and they're sharing ideas and help each other. And I would like to conclude with a picture. So that's a picture of the University of Minnesota campus, taken from the West Bank, right? And the significance about that picture was the first day of classes, this fall, right? So after being awake for a year plus, right? So actually we have an in-class instruction, right? And we can actually see people walking on campus, right? So it was a beautiful, bright day, nice, fluffy clouds, and no snow on the ground, which is always a plus, right? So I'll conclude here. Thank you.
Thank you, George. Well, that brings us to the end of this presentation. So I'm looking on Hub. There are no questions here. So that means that, George, you have solved all the problems.
Problem solved.
But I have a question I just wanted to ask you. So, obviously you've been working in graph partitioning, and you talked about, not only about matrix solvers and parallel computing. Do you have any thoughts on, and you have talked a little bit about, graph partitioning for clustering, like you talked about that. So is there anything that you want to share a little bit about how some of the technologies that you developed might be applicable for machine learning and AI?
Yeah, sure. Again, I'd be happy to do that. So after being at AWS and Amazon for about 2.5 years, I came to realize that there are a lot of partitioning problems, within Amazon at large, and actually a lot of people are using METIS. I didn't know about that, and the non-scientific computing use of partitioning, falls into a kind of a couple broad categories, right? So one has to do with resource allocation, right? And again, you're still trying to optimize for locality to some extent. Like, for example, making sure that your queries, if they need information from different tables, they will hit the same kind of storage block and so forth, right? So there's a lot of optimization on the infrastructure side. In the context of large networks and large network analysis, partitioning is used extensively as a way to kind of divide and conquer. Lack of a better analogy, right? In which what you do is you rely on a partitioning algorithm, on a clustering algorithms to find a subgraph in which you can operate on that as a reasonable good sample of the whole graph, and not have to worry about communication or dealing with a big thing. Right? There are a lot of graph partitioning applications when it comes down to knowledge modeling and workloads as it relates to graph databases. Actually, Umit recently joined our sister team that is developing the graph databases just to be able to optimize some of the workloads. So there are a lot of applications of graph partitioning or clustering at large in anything that has data and anything that has connections between data.
Okay, thank you. Let's see. So I now see a question. So let me read this. It says, what role do you think quantum will play in graph partitioning algorithms in the future? So for example, this QAOA algorithm is the quantum approximate optimization algorithm. Mm-hmm. I was hoping someone was going to ask this question because, and I did not pose this question because I was actually asking you the question. And so again, going back to, these new disruptive technologies like quantum, what do you think?
I think, I think it's a great opportunity, and I'm actually looking forward to see the extent to which they actually make a difference, right? We've been talking, some of our, my former students, involved in quantum annealing, right? And this is something that, we have been discussing on and off for the last 5+ years, right? I think there's definitely an opportunity, right? But I think, the technology will probably take some time to mature, right? But yeah, I mean, this is something that will be interesting to see what will happen there.
Okay. Another question that just popped up, it says, where will METIS go in the future? For example, what about GPU acceleration or other newer technologies to look forward to? Bottom line, what is the next METIS?
That's a very good question. Anybody's interested in joining the group so we can actually develop the next minutes? GPUs, so you guys remember my slides? So one of the slides says, new parallel computing architectures, right? So there's definitely the interest in pushing a lot of the computations into GPUs, right? And the same thing, other type of accelerators. At this point in time, many of the accelerators are designed primarily for dense computations, but that thing is changing. Some of us over here were involved with some DARPA projects that had to do with a processor that they're well suited for graph processing. So I think there is an opportunity, right, to explore and exploit hardware investments in order to accelerate these type of workloads. So,
okay, I think we are just about out of time. And again, thanks, George, for the wonderful presentation, and good to see you again.
Yep,
And
thank
so
you.
is Vipin as well. Thank you.